Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
All right, next up, we have a talk on solving random quadratic systems of equations is nearly as easy as solving linear systems by Yushin Chen and Emmanuel Candas, and Yushin will be giving the talk. Thank you.
Thank you very much, and it's my great pleasure to be speaking here. So today, the talk is about some good news about solving a quadratic system of equations, and this is showing work with my advisor, Emmanuel Candas. Okay, so what's the problem? So imagine that I have an unknown vector x, which contains n variables, and what we are given is a set of quadratic equations or quadratic measurements about this unknown object. So more precisely, suppose that we obtain m quadratic equations or quadratic measurements about this object, and in each equation, ak is the sampling vector that we are going to employ, and yk is the resulting data that we collect. So the total sample size is m. Now the question is, can we hope to recover x from this nonlinear system of equations? So this problem has found a lot of applications across different domains. So let me give you two examples. So the first example is about clustering. So consider a collection of nodes, and we are trying to partition them into two clusters based on some similarity information between some pairs of nodes. So if we use a variable either 1 or -1 to encode the cluster membership information, then this problem many times can actually be reduced to finding a solution of the following quadratic systems. In fact, in many combinatorial problems, we can always use some sort of quadratic constraints to encode some latent discrete variables. And moving from combinatorial optimization to physical sciences, and this problem has found a lot of important application, in particular in imaging applications. In many scenarios, the optical detectors or sensors are only able to record the intensities of a light with all the phase information lost because of the super high frequency of the light. So this problem, which is also called phase retrieval, it's about how to recover the phase of the measurements, or equivalently, how to recover the signal itself if we are only given intensity-only measurements, which are naturally just a set of quadratic measurements. Okay. On the other hand, the importance of this problem might be even more apparent if we look at it from a different angle. So suppose that we introduce a new variable, matrix variable capital X, use it to represent little x times little x transpose. The set of quadratic constraints we have will naturally be converted to a set of linear constraints about this new matrix variable. So essentially, solving quadratic systems is about finding a rank 1 solution based on a set of linear constraints. As a result, our efforts in solving these quadratic systems will have a lot to say about more general low-rank matrix completion problem. Okay, unfortunately, solving quadratic system is in general a very hard problem because many combinatorial hard problems can all be cast in this way. But this talk is about some good news. So if the system of equation we have has some random features, then actually there is hope that we can solve it, and actually we can solve it in linear time. Okay, so how are we going to solve it? A first impulse that came into our mind is that maybe let's try some maximum likelihood estimation, assuming that we have some statistical model about the noise. Okay. For example, if we pretend that our data is Gaussian data, and then we have some objective function that looks like a mean square error. If we have Poisson data, we also have some very simple formulation for the objective function. Unfortunately, however simple these formulations might look like, they are highly non-convex surfaces. So this means that if an algorithm is not designed carefully, it might well converge to some local stationary points which might actually be far away from the desired solution. In order to address this issue, a lot of prior work have been proposed, in particular for in the presence of random quadratic systems. So when I say random quadratic systems, I mean the sampling matrix capital A is random. Okay, so let me summarize the prior art for you. And to start with, so let me start with the sample complexity. So first of all, since we are going to recover n different unknown variables, so the sample complexity is naturally lower bounded by n. Okay. On the other hand, since even reading all the constraints, basically reading the matrix capital A, already take time m times n, so this is a lower bound for computational complexity. And now we can see where those prior algorithms are lying on this diagram. So first of all, let's look at convex realization. Convex realization is extremely powerful in terms of its statistical accuracy, and it achieves the minimal possible sample complexity, but it incurs a very large computational expense. And in order to improve this computation, there are several non-convex procedures that have been proposed, including, most remarkably, alternating minimization and Wertinger flow. But both of them are still suboptimal in some of their aspects. So in today's talk, I'm trying to propose an algorithm that can hit the lower limit for both sample complexity as well as computational cost. And this is more precisely, we propose an algorithm, which I will describe a bit later, such that provably this can succeed within linear time, and this can happen with minimal sample complexity. And this is good in theory, and this is also some procedure that is appealing in practice. And in order to show this, let me show you some numerical plots. To make some comparison, let me compare the performance, the proposed algorithm, which I will describe later, to some baseline. And this baseline, we choose it to be a strictly easier baseline, which is about solving least square problem of the same size, and using one of the most popular algorithm, which is conjugate gradient. And then I'm trying to plot relative error as a function of an iteration count. And in order to facilitate comparison, I rescale the iteration count axis so that each iteration for our algorithm is about 4 times that of the iterations for a least square problem. The good thing about this rescaling is the following. After rescaling, you can see that the error curve is almost lying on top of each other. And this gives us the message that for whatever accuracy that we want, the computational cost of our algorithm, it's just for solving quadratic system of equations, it's just about 4 times that of solving a least squared problem of the same size. And this justifies our title, which is solving random quadratic systems is not much harder than solving a least square problem. Okay, so these are the main performance that I like to show you. And what is missing is what really this algorithm is, and which I will describe to you in the rest of my talk. Okay, so this procedure, it's a non-convex procedure. And typically, a standard non-convex paradigm usually consists of 2 stages. So we start from somewhere, which is not too far away from the ground truth via some smart initialization. And this is because usually around the ground truth solution, there is a region which people call basin of attraction, such that within this region, the function we are going to optimize is still not convex, but it has a unique stationary point, which is the ground truth. So if we are able to start our algorithm from within the basin of attraction, and then if the following iterations are careful enough so that we don't jump out of this valley, and then if it converges, it might well converge to the ground truth. And our algorithm will also follow this standard paradigm. So first of all, for initialization, one of the very popular ways to do initialization is called spectral method, and which has been used in both automating minimization and Wertinger flow. So basically, it's about, so we start the algorithm using the principal component of this sample matrix. And since this is like a PCA type of scheme, And we know that if it works, it basically means that this Y matrix will attain its like almost maximum energy along the direction of the ground truth. So this is the ideal case. But unfortunately, this is not really the case unless we have a lot of data. So in practice, okay, if we don't have that many data, well, this is what we are going to get. So there are quite several directions. It's not hard to find them, such that they are far away from the ground truth, but Y has higher energy along these directions. And this is not a good news for us because this will, if we compute the principal component, it's more likely for us to get something closer to these outlier directions. And the reason that this is not good is because when we are doing PCA of Y, and Y is actually a sample average of a lot of heavy tail samples. So necessarily there are some of the samples that have too high of a leverage on the principal component. So in order to address this issue, we propose to undo this leverage by throwing away some large data. And so we run a PCA for this truncated average of the sample matrix. And this gives us some theoretical advantage. Also, more importantly, this actually has a lot of practical advantage. So let me give you some numerical example. So suppose that our ground truth, X, is this Stanford core image, which contains a lot of pixels. And if we just do spectral initialization without any trimming procedure, and this is the initial guess that we are going to get, which we can hardly see any information from it. But if we first do some trimming, which we trim a few data before we perform PCA, this is the image that we get, which you can already see a lot of information about this Stanford quote. Okay, so this is about initialization, and our next stage is about this iterative updates. And there are a lot of ways to do this stage, and one of the remarkable ways is the so-called Wertinger flow. Basically, we choose the search direction as the Wertinger gradient of the objective function. So Wertinger gradient, you can just think of it as some sort of ordinary gradient in the real, at least in the real case. But there is some issue about it. So let me try to plot all the gradient component with respect to each data to you. So this is the typical distribution of all the gradient components. And Z is my current iterate, and X is the ground truth. And you can see that there are many of the gradient components which are more or less pointing towards the right direction, which I plot in blue. But there are a few of them, which are plotted in red, that they are actually excessively large, and they are pointing towards some arbitrary direction which we don't like. And this is not a good thing because it introduces quite a lot of variability on the descent direction. So the descent direction is not really well controlled. And to address this issue, so why don't we just discard these high leverage samples before we form this descent direction? And the way we detect these outliers is, so, okay, let's look at each of the gradient component. If some of them is excessively large compared to some typical size, then we just remove it. And we will make sure that we don't remove too many. And this will be because we are discarding some data. So necessarily we are somehow introduces a little bit bias. But more importantly, we significantly reduce the variance. And this will give us the benefit. In fact, if without this trimming procedure, because the gradient component is not well controlled, and in order to avoid overshooting, we need to choose the sample size to be very small in order to avoid overshooting. But after this trimming, we get a much more stable descent direction, so we can move much faster and much more aggressively than the previous case. And this is the reason that we get great computational benefits. Okay, so to quickly summarize our algorithm, it consists of two stages: spectral initialization, following some Wertinger gradient type of update rules. In each iteration, each step, we use a more adaptive rules by discarding a small set of high leverage data in order to stabilize everything. And this gives us an enhanced performance for solving quadratic systems, and more precisely, we can rigorously prove that if the system has random features, the algorithm will start within the right basin of attraction, and after that, it converges geometrically fast to the ground truth solution. And all of this happens with minimal sample complexity. Okay, so this is showing the good result in theory, and this is also good in practice. So let's come back to our image example. So recall that after the proposed initialization, we get something that looks like this. And after we run the proposed iteration for 50 times, and then we get an image that is almost noiseless. And finally, just a quick comment about some technical difficulties. So note that we are doing some iterative procedures. So all of the iterates are highly correlated to each other. So this results in some technical difficulty. And in order to address that, many of the prior approaches require that we employ some fresh samples, new samples at each iteration in order to decouple the dependency. But the approach that we use here do not require that. We can actually handle the type of iterations where all of the iteration reuse all the samples all the time. And in many situations, and this might be the version that we actually want to run in practice. So to conclude, we have proposed an algorithm to achieve the best sample complexity and best computational cost simultaneously. And the key message is that we would like to discard high-leverage data in order to achieve a better, more stable performance. And there are quite a few things that I have no time to talk about, but I will stop here. Thank you very much.
So thank you, Chen. Before we take some questions, can I ask the Spotlight speakers to come up to the front and prepare for your talks? And do we have any questions?
Thank you for the talk. So my question is about the feature matrix. I saw you have the assumption that the features need to be independent in this case. Like, is this essential? Like, will the method still work when my features are correlated with some kind of a correlation matrix? Thanks.
So you say the matrix A, right?
Yeah, matrix A.
Okay, so what we are proving here is that when A has RID random sub-Gaussian features, we can do that. But this is not very crucial for the algorithm to work. At least, for example, for many of the cases, we just need this matrix to has some sort of incoherence. So we don't actually, I mean, this cannot be something like an identity matrix, something like that, which is highly structured. But if this is sort of like unstructured and has a lot of incoherence property, then it should work. So for example, some sort of like restricted isometry property, some sort of like that. But this can well beyond this ID Gaussian model. Thank you.
Another question? So your contribution combines an initialization step and the truncated gradient step. Mm-hmm. Can you sort of qualitatively split these into how much of an effect both the two steps have on the overall performance?
So if we do this truncation step, let's say for initialization, the computational cost is almost the same, but it will affect your sample complexity by a lot. And for second stage, if you do this regularization things, it will affect both computational cost as well as the sample complexity. In particular, for computational cost, there will be a gap of as large as order n if you don't do any trimming things.
Do we have any further questions? In that case, let's thank the speaker again and move on to the spotlights.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.